Hello there, students and friends. Welcome to my lecture series on alternating current. This first episode focuses on analyzing inductor in series with an AC voltage source, a capacitor in series with an AC voltage source, and a resistor and capacitor in an AC circuit. How does each of these elements behave in an AC circuit? Find out, stay tuned, watch and learn. If the voltage source in a circuit is AC, like an AC generator shown in the figure, we describe the voltage and the current to be sinusoidal, or they move in simple harmonic motion. So this means that the voltage changes in both magnitude and directions as time changes. This is shown in the figure here, the graph voltage versus time, right? So as shown in this figure, the voltage increases, say for example, from 0 to a maximum positive value. Then it decreases back to 0 and then increases to a maximum negative value. And finally, it decreases again to 0. That makes one complete cycle. So, in the equation for determining the instantaneous voltage, as well as in determining the instantaneous current, you will notice that both the voltage and the current are expressed in the cosine function. Right? The meaning of each of these quantities uh, is given here. Small letter v stands for the instantaneous potential difference at any given time t. Capital V refers to the voltage amplitude or the maximum potential difference. Small letter I is the instantaneous current, all right, which is changing. So if you want to find the instantaneous current at any given time, that is the formula to use. Capital I, of course, refers to the current amplitude, which is the maximum value of the current. Of course, omega refers to the angular frequency of the oscillation, which, as we know, is equal to 2 pi times the frequency f. And finally, the small letter t refers to the time or the instant. For example, if you're looking for the current at any given time or instant. We express the instantaneous voltage and instantaneous current in terms of the cosine function. Why is this so? All right. Um, let's take the case of the sinusoidal current, small letter I. It is expressed as uh, the product of big I or capital I, which stands for the maximum current, and the cosine value of uh, omega t. Okay, the product omega t refers to the angle expressed in radian. All right. Now, as shown in this figure, all right, we call this a phasor diagram. And when we say that I, small I is equal to capital I cosine omega t, all right, It is, or it can be explained using this phasor diagram, an example of which is the phasor current. And the phasor current is represented here by this arrow in the first quadrant. Okay, the length of this arrow represents or is equal to the maximum value of the current I. We say that this phasor is rotating in a counterclockwise direction. Okay, um, it is rotating with a frequency small f and an angular speed omega equal to 2 pi f. Okay, the angle that this phasor makes with the horizontal is labeled here as omega t, which actually refers to the angle. All right. When omega is multiplied by time t, that represents uh, the angle in radian. Okay. Now, um, why it is cosine? It is because this phasor, okay, or the projection of the phasor into the horizontal axis at time t is represented by this arrow along the horizontal or x-axis. All right. And if you're going to represent the value of that current, the projection of the phasor along the x, okay, we just use cosine or multiply the value of the maximum current, capital I, and the cosine of uh, the angle omega times t. So that's the reason why uh, the equation for determining the instantaneous current I is expressed in the cosine function. And that goes through also for the instantaneous voltage. All right. Small v is also equal to capital V, which is the voltage amplitude, the maximum value of the voltage, multiplied by the cosine of the angle omega times t. All right. So we'll be discussing more about this, uh, the phasor, the concept of phasor, in one of the problems that we're going to discuss later. So, what are the quantities here in these formulas? We have them defined earlier, all right? Inasmuch as the voltage as well as the current, okay, at any given time is not constant, okay, the small current I is always dependent, of course, on the maximum current as well as the value of the cosine of the angle. All right. So this brings us to the concept of what we call root mean square or RMS values. For example, in the case of current, the root mean square value of the current I is just equal to the maximum current I divided by square root of 2. And for the root mean square of the voltage or V of RMS, it is also equal to the maximum voltage or the voltage amplitude divided by square root of 2. Right? And the voltage across our household wall out sockets is mostly 220 volts here in the Philippines. All right. Uh, in other countries like in the US, I think they use 120 volts. Now, these 220 volts as the voltage in most um, wall sockets, this is in fact the root mean square value of the voltage. All right? It is not the maximum value of the voltage. Based on this formula, if you want to determine the maximum value of the voltage, capital V. Alright, we just isolate, and that will be equal to the square root of 2 multiplied by the root mean square value of the voltage, such as 220 volts in the Philippines. Alright, so let's try substituting square root of 2 multiplied by 220 volts. It will give us positive or negative 311 volts. What does this mean? This means that 60 times per second, that's the frequency, okay, used in the Philippines for an AC circuit. 60 times per second, okay, uh, the instantaneous voltage or the voltage small v across a socket's terminals, like the one shown here, it varies from 300 or positive 311 volts to negative 311 volts and then back again, okay, 60 times per second. So in one cycle, we can imagine that the voltage is fluctuating, okay, fluctuating from positive 311 volts to negative 311 volts. But the root mean square value, we say, is 220 volts. Well, in the US, it is the root mean square of the voltage of most of the household socket is 120 volts. We now have our question number 1. The user's manual of a student's notebook says that it draws 2.5 amperes from a 220 volts 60 Hz line. For this notebook, what are letter A, the average current, letter B, the average of the square of the current, and letter C, the current amplitude? Alright, so here's our solutions and answers. For the first question, the average of any sinusoidally varying quantity over any whole number of cycles is, of course, equal to 0. Now, for question letter B, we first recall the definition of the root mean square of the current, labeled here as I sub RMS, which is just the square root of the mean of the square of the current, alright, labeled as small letter I squared subscript average. Alright, so that value for the RMS current is actually given in the problem. It's equal to 2.5 amperes. Alright, and we can equate that to the square root of the small letter I squared. Alright, we call that the square root of the mean of the square of the current. And what we're going to find is in fact the square of I sub RMS, right? So substituting the value of RMS current, which is 2.5 amperes, get square that, and we will get the value, right? Which is 6.3 amperes squared. That's the answer to letter, or to question letter B. And for question letter C, we're looking for the current amplitude, capital I. And based from the definition of the root mean square current, which is equal to the current amplitude, capital I, divided by square root of 2, all right? So we again isolate capital I, which is the current amplitude. That will become I equals square root of 2 multiplied by the root mean square value of the current. Substituting, we have square root of 2 multiplied by 2.5 amperes. So our answer is that the current amplitude equals 3.5 amperes. Okay, moving on to question number 2, which is about an inductor in an AC circuit, just like what is shown in this diagram. So, an inductor with inductance capital L equal to 2.50 millihenry is part of the circuit for an aviation radio beacon that operates at 108 megahertz. Questions. Letter A. Find the inductive reactance of the inductor. And question letter B. Find the amplitude of the current in the inductor if the amplitude of the voltage across the inductor is 4.20 kilovolts. Alright, so for our solution, we first determine the angular frequency of the oscillation, omega, which is 2 pi times the regular frequency f. That means 2 pi multiplied by the given frequency f. 108 megahertz is 108 times 10 to the 6 hertz. So we will get our value for the omega equal to 6.78 times 10 to the 8 radian per second. So we can now find the inductive reactance. Question letter A. The reactive or the inductive reactance of the inductor, labeled capital X sub L, which is just equal to the product of omega and the given inductance capital L. So when we substitute, all right, the calculated omega, which is 6.78 times 10 to the 8 radian per second, multiplied by the given inductance, already in Henry, 2.50 times 10 to the negative 3 Henry. So we get the value of the inductive reactance, capital X sub L, equal to 1.70 times 10 to the 6 ohms. For question letter B, finding the amplitude of the current, right, in the inductor. So that's expressed here in terms of capital I being equal to uh, the amplitude of the voltage labeled capital V sub L divided by the inductive uh, reactance, capital X sub L. Substituting, we have 4.20 times 10 to the third volts. That's the value of the voltage amplitude divided by 1.70 times 10 to the 6 ohms. This is the inductive reactance that we just calculated in letter A. So simplifying, we will get the value of the maximum amount of current in the inductor, also called the amplitude or the current amplitude, which is equal to 2.47 times 10 to the negative 3 amperes, or simply equal to 2.47 milliamperes. So, before we go to our last question, let's first emphasize the concepts that we have applied in this question, right? Number one, in general, the lower the frequency of an oscillating voltage applied across an inductor, the greater the amplitude of the resulting oscillating current. Okay? Number two, for any component in an AC circuit, the reactance is the ratio of the amplitude of the voltage across the component to the amplitude of the current through the component. If the component is an inductor, the reactance equals the product of the inductance and the angular frequency of the current. That means uh, the inductive reactance labeled as capital X sub L is just equal to the product of the angular frequency omega and the value of the inductance capital L. So our last question, question number 3, which is about a resistor and a capacitor in an AC circuit, just like what is shown in this circuit diagram. So an AC circuit includes a resistor with capital R equal to 125 ohms connected in series with a capacitor whose value is equal to 7.00 microfarad. The current through the resistor and the capacitor, which is labeled as small letter I and expressed as a function of time, equal to 2.40 times 10 to the negative 3 ampere times the cosine of 1.75 times 10 to the third radian per second multiplied by the time t. Questions. Letter A, find the voltage across the resistor as a function of time. Question letter B, find the capacitive reactance of the capacitor. And question letter C, find the voltage across the capacitor as a function of time. Alright, so our solution to question letter A, we're looking for the instantaneous voltage across the resistor big R using the formula small current I multiplied by the big resistance R. Right? In the question, we are given the equation that determines the value of the current small I. Right? So that is exactly what we are going to use also for determining the instantaneous voltage across the big R. Then multiply it by the given value of the resistance. We just substitute that into this equation and we will get, alright, so 2.40 times 10 to the negative 3 amperes to be multiplied by the cosine of 1.75 times 10 to the third radian per second multiplied by the value of the time t and then multiplied by the given resistance of 125 ohms. So we just simplify this equation by multiplying the value of the resistance to the maximum value of the current or the current amplitude 2.40 times 10 to the negative 3 amperes. Right? So the simplified equation now becomes 0.300 volts. Right? Multiplied by the cosine of the angular frequency, which is 1.75 times 10 to the third power radian per second multiplied by time t. And this is what is required in the question. An equation that defines the instantaneous voltage across the big R. Now for letter B, question letter B is asking for the capacitive reactance, all right, uh, labeled here as capital X sub C. And that is just equal to the reciprocal of the product of the angular frequency omega and the capacitance capital C. Substituting, we will get 1 over 1.75 raised to the third power radian per second times 7.00 times 10 to the negative 6 farad. Alright, simplifying, we will get the value of capital X sub C, or the capacitive reactance, which is equal to 81.6 ohms. That's the answer to question letter B, the capacitive reactance in the capacitor. Alright, for the last or final question, letter C, we are actually looking for the instantaneous voltage in the capacitor, okay, at any given time. So we are asked to find an expression or equation that determines this instantaneous voltage. But before we can do that, we will first determine the capacitor voltage amplitude, denoted by capital B sub C. And that is equal to the product of the current amplitude, capital I, and the capacitive reactance, capital X sub C. That is, the capacitor voltage amplitude is equal to 2.40 times 10 to the negative 3 amperes multiplied by 81.6 ohms. This is the value of the reactive or the capacitive reactance earlier calculated in letter B. Alright, so multiplying these two numbers, we will get the value for V sub C equal to 0.196 volts. And our target variable, which is the voltage capacitor small letter V sub C, it's actually equal to capital V, which is the capacitor voltage amplitude, times the cosine of omega t minus 90 degrees. Right? What does this minus 90 degrees, what does this suggest? All right. If you look at our phasor diagram, we have here the current phasor, right? The current phasor, which is represented here by the arrow colored violet, all right? That's the current phasor, while the voltage phasor is the one colored red in the fourth quadrant, right? Uh, in a capacitor that is connected to an AC source, all right, the voltage and the current are not in phase, all right? We say that the voltage phasor, the one in the fourth quadrant, lags the current phasor by an angle or phase angle phi equal to negative pi over 2 radian, or negative 90 degrees. So that is the meaning of the minus 90 degrees in this equation for B sub C. All right? But to be consistent with our previous notations, this 90-degree angle expressed in degrees has to be converted to radian. That's just equal to negative pi over 2 radian. Therefore, our final answer, okay, an equation that gives the instantaneous voltage in the capacitor as a function of time can be equated, all right, as 0.196 volts. All right, that is the voltage amplitude multiplied by the cosine of the angular frequency omega 1.75 times 10 to the third radian per second multiplied by uh, the time t minus, right, included in the bracket is minus pi over 2 radian. So there is a bracket, uh, the cosine of the quantity 1.75 times 10 to the third radian per second multiplied by t minus pi over 2 radian before you multiply to 0.196 volts. All right? So, before we end, here's the key concept that we applied in this question. The reactance, or the ratio of the voltage amplitude to the current amplitude for a resistor in an AC circuit is equal to its reactance. For a capacitor, right, just like in this problem, the reactance, or we call it the capacitive reactance, is just equal to the reciprocal, the product, the capacitance, and the angular frequency of the current. That is capital X sub C, or the capacitive reactance, is just equal to 1 over the product of omega and capital C. So that's it. We are done with our tutorial. Thank you very much as usual. Thank you very much for watching. Please follow me